Hi guys, welcome to this tutorial. Today I am going to show you the practical implementation of Generative Adversarial Network, or GAN in short. There are many variations of generative model, and today I am going to show you DC GAN, Deep Convolutional Generative Adversarial Network. GAN architecture mainly consists of two models. One is generator and the second is a discriminator. Here the discriminator is a pure convolutional neural network, and the generator model will be trained using this discriminator. The generator model is not a complete model in this standalone form. I will explain you how the generator is getting trained using the discriminator, and finally how the generator alone can create images which is having the same statistics as the training set. Okay, let's get started. So today I'm going to use a Google Collab notebook for the training or developing this architecture, because in Collab notebook there is an option to select the GPU, because the computing power required to train a GAN network is very high. So if you use your laptop or CPU, then it may take days to complete the training. Depends on the number of the layers, or the number depends on the model you have created and the number of images. To select the hardware accelerator, you have to go to runtime, and there is an option to change runtime type. Go to here, hardware accelerator. I already have selected the GPU. There are options to select GPU, and by default it will be CPU, none, and the TPU option also there. I have selected GPU today. And next step is to import all the required libraries, and I am using Keras library to develop that model. Run this block. All libraries have been imported. Next, I have written a function to load the images. So here in the Collab notebook, I have created a folder, and today I am going to use docs images which I have downloaded from Kaggle competition site. There are many images, around 25,000 images of cats and dogs, and from that I have downloaded to train this model. In this function there are two parameters. One is the directory, and the second is number of images to be returned. So here I have used that OpenCV imread method to read the files from the folder, and then you have to convert, because OpenCV returns image in that BGR format. So if you display in that BGR format, it will be kind of a weird color. It will be showing up. So first you need to convert in RGB, and for that there is a method in OpenCV convert color, CVT color, and passing these parameters. Then next we need to convert that into a numpy array, and returning this function is returning that numpy array, images array. Now I am calling load images function, and setting the return value, the list of images, to a images variable. Control enter. Okay, when you are using a directory from the Collab notebook, first you need to mount that drive before using that. So initially you have to mount, then only you will be able to access that. For that you can use that mount method available in the drive library google.collab. So run that, then you will get a URL. Click on that, it will be directing to a folder for authentication. Click on your Google account, then there will be allow button. Click on that. You need to copy this string and paste there in this text box. Enter. Now the authentication in process, you will have access to that content / drive folder. So if we check that again, you can say drive already mounted at this this drive. So execute that load images again. It will take some time to load the images. Now the images has been loaded to this variable, and to display a few images, I am looping through images and using that pyplot. I'm displaying some images. Here you can see the dog's images which are in different shapes, or we can say that some dogs images are showing faces clearly and some whole body is there, and using this type of images for training will not give a better result to what we are expecting, like a dog's image. Generator won't be able to generate or create the images which we are expecting as a dog, but yeah, there will be, but we may have to use a lot of image samples for training. Here I am using just 12,500 images to train the model. That may not be sufficient, but let's see how it is. Here my intention is to show you how to train, how to create the models, and how to train that generator using that discriminator, how eventually how it can generate the images as a standalone model. Now we will start creating that model. First we have to define the discriminator model. Here the discriminator model is just a regular deep neural network. Here I'm using that Keras sequential model and then adding the layers. I have added 4 layers and the 1 input layers and 4 hidden layers. So in this first input layer, I have used 64 filters with a kernel size of 3 by 3, and setting the padding same, so that it will add the padding so that it will we will get the output as same as the input. And input shape I am passing as a 128 by 128 by 3. This is for channels, RGB channels, and the shape, height and width are 128 by 128 pixels. And here the activation function I have used is leaky ReLU instead of ReLU with a slope of 0.2. This is the best practice which is researchers found getting a best result for GAN model. And then added 4 hidden layers having the same settings, 64 filters and a kernel size of 3 by 3 and strides. Here one thing you need to notice is that the strides I have set 2 by 2 and no pooling layers have been used. This is this stride setting. Instead of 1 by 1, the default setting, I have made that as a 2 by 2. This is for downsampling. Instead of using that, it will give a similar impact of doing that pooling. So instead of pooling, I have used that strides, and this again that best practice suggested by the researchers in this field. So 4 hidden layers, and then finally before connecting to fully connected layer, so we are doing that to flatten, and then a dropout for regularization 0.4, and then adding a fully connected layer, dense layer with a 1 neuron output and activation function sigmoid. So here I have used that Adam optimizer, which is based on the stochastic gradient descent, and for the loss binary cross entropy, because it is the output is binary, true or false, whether it's a fake image or a real image. So that's a classification, binary classification. So the loss function we have used is binary cross entropy. And metrics, we are interested in the accuracy metrics, and return this model. Let's see the structure of this discriminator. For that, create an instance of this discriminator model. And then see that model dot summary, and here you can see that each layers, the input layer, we are passing size, data size of 128 by 28 into 3, and here the shape after the first convolution, because we are using that 64 filters in each layer. So it is the size has been, the channels has been increased as 64 corresponding to each filter. And you can notice here the size, the height and width of neurons in each channel, it has been reduced by half. So 128, that is in the input channel, after the first convolution it became 64 by 64. That is because we have configured for a stride of 2. Because of this, it is giving the same effect of doing a pooling. So now after this convolution, the final in the last layer, that hidden layer, the size became 80 into 80 into 64. Now in the next layer, in the flattened layer, we are making that as a scalar, and then that is passing to that output layer and giving the final result or the output from the discriminator. Next, I am defining the generator model. This is a little different from the discriminator. The generator input is a point in latent space. The latent space is a randomly defined vector space of Gaussian distributed values. So that means it has no meaning, but by drawing points from this space randomly and providing them to the generator model during training, it will the generator will assign some meaning to this input values, and finally that will be converted into the image. Basically, it is randomly generated points in normal distribution. That means having mean 0 and standard deviation 1. I will show you how it is created, randomly generating these points in this latent vector space, and how it is passing to that generator model. Here the model is similar to that discriminator. We are we are creating an instance of sequential model, and the nodes, input nodes, we are not just passing one low dimension version of the image. Instead of that, we are passing a batch of here I have selected 256, a batch of 256 images, not image, it is a latent space points, but that will be parallelly passed. So it will be having many parallel filters, resulting in multiple parallel activation maps. So it is known as that feature map. So here the batch of images, the inputs will be processed parallelly using these filters, and model adding the first dense layer. Input layer is a dense layer with input dimension as this latent dimension, which we are passing as a parameter, input parameter. And here also we are using a leaky ReLU as activation function with a slope of 0.2. Then we have to reshape these for number of rows, columns, and the channels, 256 batch or channels here. That is that many number of parallel processing happens using that many filters. So here then the next step is we need to upsample from 8 into 8 we need to upsample, that is to 16 into double. Earlier we have downsample in that discriminator. Here we will be doing that reverse operation. So here the low resolution image will be converted into higher resolution version of that image. There are two ways to do this upsampling, and it is also known as deconvolution. It is the reverse of convolution. And one way is using that upsampling 2D layer. So here you can see you can add upsampling 2D layer, or that is one way. And then after this you can use, or this should be this upsampling 2D should be followed by the normal convolutional 2D layer. That is one way. And another is here, which I have used using a transpose layer. Here you can see that convolutional 2D transpose. This layer will do the same. It will upsample and do a convolution. And here the filters used is 128 filters, and with a kernel size 4x4, and the same way the strides 2x2 stride, so that it will double, because we are doing this the reverse process of convolution, so convolutional transpose, so it will double the size of the image, input images. And the padding, same padding, so that the size will remain same, input and output size, so it will add padding. Same way that activation function we have used leaky ReLU. And one thing you have to notice here is we are not compiling this generator model here, and so there is no loss function or optimization algorithm specified here, because we are not directly training this generator as a standalone model. This this generator is trained using the discriminator in the combined mode. Now we will see that details of this generator model by creating an instance of this model and seeing the summary. Okay, first we need to run this. And control enter. Yeah, okay. So here the input size we are passing as the initial input is the latent space points 8 by 8, the 250 as a batch of 256 samples. And now after the first transpose convolution, it became double, the size became double. And finally you can see the image size. It is generating an image from a latent space of this size 8 by 8 into 128 by 28 by 3 channels. To convert the image into this dimension 128 by 128 by 3, we have added this convolutional 2D layer with 3 filters. Here we are in this layer, we are using that TANH hyperbolic tan activation function with the padding setting as same. Now we have to combine both the models. This is the GAN architecture. Here the trainable property of discriminator object model is set as false because the weight should not be updated inside this combined model. The discriminator model is trained separately using real and fake images as a standalone model. The optimizer is set as the Adam set as Adam, and the loss function binary cross entropy. Run the function. We can see that summary. Here you can see that output shape of generator is the the image size 128 by 128, and the discriminator model output shape is 1, indicating whether it's a real or fake image. Next, I have written a function to load real images from the directory. Here I have used image data generator method that is there in the keras.preprocessing library, and you have to pass the folder, and all the images inside that folder will be returned using this method call. And since we have set that image size, input image size of the discriminator as 128 by 128, I have resized the image from here, setting the size, target size. You can use any options to grab data from the directory, the images from the directory. For example, that list directory, list dir from IO library you can use. Then we have to convert that image array into a numpy array and returning that. So next we need to write a function to generate real images using the images returned from the above function. We have to fetch a batch of images as per the parameters we are passing. This data set is the image array images which we got from the previous function, and here generating that random numbers, and then using that random numbers it is picking from the array and returning. So next we have to write a function to generate latent points. As I mentioned earlier, latent points are the points, randomly generated points defined in the vector space of that will have a Gaussian distributed values. Here I have used random.randn, that is to generate a normal distribution random numbers. So the dimension we have the dimension is passed, latent space dimension is passed as a parameter, and a number of samples required. So that will return the number of the latent space vector. Now we have to generate the fake images, which is generated by the generator model. So here the generator model is passed as a parameter and a latent dimension, number of samples required. Using the predict method of the generator model, we are generating the fake images. For that the latent space points which we have generated using the above function, that will be used as a parameter to generate the fake images, and the label we are setting that as 0 for fake images, 0, and the real images we are setting as a 1. So it will return that fake images and the label corresponding to that. Now we have to combine both the models. This is the GAN architecture. Here the trainable property of discriminator object model is set as false because the weight should not be updated inside this combined model. The discriminator model is trained separately using real and fake images as a standalone model. The optimizer is set as set as Adam, and the loss function binary cross entropy. Run the function. We can see that summary. Here you can see that output shape of generator is the image size 128 by 128, and the discriminator model output shape is 1, indicating whether it's a real or fake image. Next I have written a function to load real images from the directory. Here I have used image data generator method that is there in the keras.preprocessing library, and you have to pass the folder, and all the images inside that folder will be returned using this method call. And since we have set that image size, input image size of the discriminator as 128 by 128, I have resized the image from here, setting the size, target size. You can use any options to grab data from the directory, the images from the directory. For example, that list directory, list dir from IO library you can use. Then we have to convert that image array into a numpy array and returning that. So next we need to write a function to generate real images using the images returned from the above function. We have to fetch a batch of images as per the parameters we are passing. This data set is the image array images which we got from the previous function, and here generating that random numbers, and then using that random numbers it is picking from the array and returning. So next we have to write a function to generate latent points. As I mentioned earlier, latent points are the points, randomly generated points defined in the vector space of that will have a Gaussian distributed values. Here I have used random.randn, that is to generate a normal distribution random numbers. So the dimension we have, the dimension is passed, latent space dimension is passed as a parameter, and a number of samples required. So that will return the number of the latent space vector. Now we have to generate the fake images, which is generated by the generator model. So here the generator model is passed as a parameter and a latent dimension, number of samples required. Using the predict method of the generator model, we are generating the fake images. For that the latent space points which we have generated using the above function, that will be used as a parameter to generate the fake images. And the label we are setting that as 0 for fake images, 0, and the real images we are setting as a 1. So it will return that fake images and the label corresponding to that. This function is used to evaluate GAN performance. Because the generator is using unsupervised learning algorithms, we cannot calculate this objective error score for generated images. Instead, we should manually evaluate for the image quality. That means we don't know when to stop the training without looking at the examples of generated images. For that, we are periodically evaluating the classification accuracy of the discriminator on real and fake images, and periodically saving the generator model. Run this code block. Last step is train the GAN model. Here this function train GAN, which is accepting generator model, discriminator model, GAN dataset. This is the image dataset. Latent dimension epochs. It is by default we have set as 100, and batch size 128. Here the batch size total batch size is 256. Here 128 real images and 128 fake images we are passing. First we need to calculate a batch per epoch. For that the total number of images divided by the number of batches, sorry, batch count. Here it is 128 total number of images, that is 12,500 divided by 128. And then we have to manually enumerate through epochs. There are by default we have set as 100 epochs, so it will loop through 100 times by taking this batch size. So that's why we have two for loops. One is for number of epochs and this is for batch inside that epoch. First we have to generate the real images, setting these variables x real and y real, calling that generate real images, passing the data set and batch size 128, and then creating the fake images using the function generate fake image. And then we are doing that vertical stack. So here the count is, as I told you, the total batch size is 256. Here 128 real images and 128 fake images. So we are stacking that as a single set. Then calling model discriminator train on batch, passing these xy parameters. Hence the discriminator model has been trained as a standalone model and weights has been adjusted now to classify real and fake images. Next step is train the GAN model. For that we have to create latent points using this function generate latent points, passing the latent dimension and batch size. And then we are setting that the fake image y value as 1. The reason being, we have set the trainable property of the discriminator as false, so its weight cannot be updated. The GAN model will classify the fake image as 0, but the actual value we are passing as 1, and hence the model will find a huge error between actual value and the predicted value, and it will try to reduce the error by adjusting the weights. Since the GAN can only adjust generator neuron weight, it will do so to produce near real images. That is how we are training the generator. Here it is calling that model GAN train on batch, passing that GAN x and y, and then printing that the loss and epoch counts. And here calling that for every 10 epochs we are calling that a function to save the generator model and showing that loss, sorry, a discriminator accuracy. Now we have done with creating all the models. Then next step is to train the GAN model. For that we are declaring that setting that latent dimension as 100 and creating objects model object and GAN discriminator model. Then calling the load real images and setting that to data set variable. Running that. It is going to take some time to load the images. So I will pause the video, and once it is completed I will come back and will continue. Welcome back. I have completed loading the images and also ran this train GAN, this function to train the GAN model. It took around 4 or 5 hours to complete that, the entire process, training process. And I will show you, I will load that my saved images. I'm setting to that same variable model underscore g. That is the generator model we have trained in using that GAN. Now there is a function written to plot the images. So I'll be plotting 9 images in line. So when I run this function, when I call this passing latent points, so this generate latent points. We already have seen this to generate latent points, and then calling the model G dot predict, passing these latent points, and then plotting the images. Yeah, here we have generated some images, dogs images. It is hard to identify, and we'll run this again. We'll see different images will be created in each run. So kind of, because there are many reasons why we are getting this. One is, as I told you in the beginning, the dogs images which are all of different types, and it is not consistent. So, and the number of images also, that also matters in the training. Now we will show you the outcome of a generator, which the same model, GAN model, I have used to train the faces, celebrity faces. There were around 1 lakhs, more than 1 lakhs images are there, but I have used 25,000 images, face images, and using the same model I have trained, and I ran 79 epochs because it was taking a long time. I could only run 75 epochs, and I will show you that I'm just using that model, the generator. Now running that, using that model, I'm using the same latent points and running this, showing that images, so the face images. Now you can see that how the generator is creating the face images. See, it is almost like I haven't even completed 100 epochs. So in 79 we got a pretty good pictures. It is automatically creating by the generator. The fake, actually there is no real images corresponding to that. The generator, it's on creating these faces. This is the beauty of GAN architecture. That's all for today. Thank you very much for watching this video. If you have any comments or any questions, please let me know.